Welcome back. I would like to talk about motion planning, and I am going to use waypoints, okay? So when you use waypoints for motion planning, this applies that you have a known environment, right? You know the location of the obstacles like this, and you know the starting from some initial condition, you know the places that you are going to visit. So when you have a known environment, I am going to cover what happens if the environment is partially known or unknown in the next video, which I am not going to use waypoints. So basically, here, when we talk about motion planning or path trajectory planning, I would like to define it. It is the field of robotics that deals with the task of determining a sequence of configurations that moves a system from one configuration to another, right? So we would like to move our robot, in this case, two-dimensional case. You can do three-dimensional case as well. And when we specify this motion planning with waypoints, again, we know the environment, and it refers to the scenario that a system visits each waypoint, or on a ballpark, a neighborhood of these waypoints while moving through this known environment. All right. So I will directly start with these points, right? If you look at the first point, it is x0, y0. Let's look at the second point, x is 1, y is 2. So x is 1, y is 2, so on and so forth. So if you look at the fifth point, for example, right? The fifth point, x is 2, y value is 9. So I want my vehicle to visit those points, and I would like to generate a path for it to visit. So your robot basically, in addition to the x and y, it is important that you need to define a time that your robot initially at 0, 0. Let's say at 1 second you want to visit the first waypoint. In 2 seconds you would like to visit the third point. So basically in every second, right? 1 second, 2 second, 3 second, you visit a point. Of course, I mean, this is just for this example. Actually, it depends on your robot dynamics. For example, maybe, if you are looking for example, small ground robot, and if these are in meters, let's say you want your robot to move 1 meter in X and 2 meters in Y, it can take about, depending on the robot, 5 to 15 seconds. So right now, again, think these numbers as times as some generic numbers. It can be 10 seconds, 20 seconds, 30 seconds, so on and so forth. All right. Now, this is a curve fitting, and we can use the materials that I cover on these lectures on regression and control. Basically, you can use non-parametric models versus you can watch these videos, constraint function construction, and part 1 and part 2. So if you want to pass through given waypoints exactly, I would like to use the ideas from this constraint function construction. Otherwise, if in general, right, if this is a quadcopter flying through an environment, on a ballpark, you don't have to pass through exactly these waypoints. You can approximately pass. So in general, when I do, when I deal with such motion planning, I generally use non-parametric models. But if I really would like to pass, not approximately, but if I want to pass exactly for given points, I use constraint function construction. So if you watch these two videos, you may think, well, all these videos, right, we did curve fitting, least squares, or gradient descent. We just did two-dimensional curve fitting. Here we are dealing with a three-dimensional data, right? In time t, you would like to, so how the previous stuff that we did on curve fitting generalizes to this three-dimensional case, or if you also add z, right, for 3D path planning, now you have a four-dimensional case. All right, the solution actually is quite simple. Let me explain. First of all, what are our independent and dependent variables? To construct a path for the desired motion, we need, right, at time 0, we need to pass through x and y. So in this case, time is the independent variable and x and y are the dependent variables. So basically what I'm trying to say, we would like to do fit between t and x and t and y. With regard to each dependent variable, we would like to generate two non-parametric models, one for tx and another for ty. So you can represent mathematically like this. I am going to use a notation similar to the previous videos that you saw. So we want x hat to be this time basis function. In this case, since we are dealing with a non-parametric model, we have a bias and radial basis functions. And we are going to use the same basis here, exactly the same basis. And we are going to find different sets of weights for t and y and different sets of weights for t and x. And we are going to find y hat. All right, and these are coming from the previous videos. Basically, this is the structure of the omega, right? This is the structure of x. So this is how you find the analytical solution for W1. Your x vector here is here, and this is y. Your y vector is here. Inside you put the basically time values. Again, I covered non-parametric models as well as the function construction, constraint function construction in three different videos. With all the videos has both the theory as well as the numerical MATLAB examples. If you haven't watched them, after you watch them, this makes a lot of sense. If you already watched those videos, what I'm explaining here should be trivial. If not, if you have any questions, leave a comments on and I can answer as I answer all the questions. All right. So following this step, we have found analytical solution to the least squares problem. Again, you can also investigate if you like gradient descent. Why not? All right. So let's start with the example. So these are the t, x, y points. I am basically putting these radial basis functions and a bias to construct the omega. In this case, we have 13 waypoints, including to the initial waypoint. That's why we have 13 here. And basically, since the time is changing between 0 and 12, I included a radial basis function changing from 0 to 12. If you think like this, right, this is t. At 0, we have a radial basis function. Then at minus 1.5, which makes this point 1.5, you have another radial basis 3, another one, all the way up to 12. You have the final radial basis function. So using x, I find the first weight and that connects t and x. And using y, I find the second unknown weight that connects t and y. And this is the simulating the motion plan. Again, this is your xp, this is your xy, basically between 0 and 12 seconds. And I am recording this data. In an application, this generated path will represent commands that you apply to a physical system, right? So think about, this is the command that you want your x position to track. This is the command for your y position to track. So the nice thing about non-parametric models using radial basis function, when you track motion, when you plan motion, in addition to the position commands in x and y, you also may need to provide their derivatives, their velocities or their accelerations, meaning that not only you provide x position command and y position command to the system, you may also need to send xp dot, same for y. So the advantage of radial basis functions is they are differentiable. They are sufficiently smooth. You can take the derivatives as many as you want. So you can take the derivative, you have the velocity command. You take the derivative, you have the acceleration command. So for applications that you not only provide x and y commands to the system, if you also need to provide their velocities or acceleration versions, non-parametric models are awesome. As this being said, As I covered in the constraint function construction videos, you can include constraints of basically delta prime to make them sufficiently continuous as well. Again, I don't want to make a longer discussion. This is just the plotting purpose. As I always do, I include the plots. And if you like my style, subscribe to the channel, give a comment, turn notifications on so that it will be awesome. And I always like your comments. All right, let's see what's going on. So basically, this is the generated path using non-parametric model radial basis function neural network. As you see here, robot, this is the comment, right? The comment that I need to apply to the inner loop. So basically, how I am applying these to the inner loop, if you want me to do a video, please let me know, right? These are just generated comments. So basically, if you make your system to track these comments pretty smoothly, pretty fast, so your system will go like this based on its dynamics and visit these points. And we are again we are using neural networks radial basis functions. We are not exactly touching these points, but you can include more radial basis functions to make this curve fitting much more close. But if I am planning an application and if I would like to visit these waypoints approximately, this is very nice. This is if you plot with respect to the time, right? At time 0, you are here. As you progress, you are basically, as you go through time 12, you go to this point. All right, take care.